Okay. Okay. Folks, guys. Okay, so in the last couple of classes, we were looking at this fellow, and we saw what is the differential mode gain, what is the common mode gain, etc. And if you want to recollect, if the differential mode gain, what was this equal to? It's minus or plus? Check carefully. If let us say I call this as a plus and minus, this was plus gm of the NMOS times the RDS of the PMOS. This is of course ignoring the channel length modulation for the NMOS transistor. And actually, if you include the channel length modulation for the NMOS transistor also, you will find that this is RDS and parallel RDS of the PMOS. Again, so you take it as an exercise and try to find out what is the output resistance of this fellow. So it will turn out to be the parallel combination of the RDS of the PMOS and NMOS transistor. But the thing to notice, you please work out, this is not parallel combination of this, because looking up we have RDSP, and looking down it is RDSN. That is not the reason. You please work out. So it comes in a slightly convolved way, but the result turns out to be this. Okay. But if someone asks you what is the looking down impedance, that is not RDS of the NMOS. You work out and you find out what is it. It's like saying 2 plus 2 is 4, 1 plus 3 is 4. The end result is the same, but the actual, what's happening inside is completely different. Okay. And we also looked at the common mode gain, and we saw that if I apply a common mode excitation to this fellow, let us say I apply some VC and VC, what can you say about the drain voltages of the two sides? They are exactly same, so we could chart this. So for common mode, we can basically simplify it like this. Let us say the current source has some Rx. So what is the common mode gain approximately? Can you tell me? From this minus? Yeah, again remember the resistance of this fellow is 1 by 2 GMP. So if I apply a voltage VC, approximately this is also VC, source follower. So current is VC by Rx. So which means the voltage here is minus VC by Rx times that resistance, which is minus 1 by 2 GMP. That is the resistance divided by Rx. This is what we got. So again, I am just telling you quick ways to remember the result, that's all. Then in the last class, we also looked at what happens for DC operating point. And let us say if I apply a bias voltage VB, what can you say about the currents in the two transistors? If the tail current is I0, what did we see for the currents in the two transistors? They are exactly getting split. We kind of proved it by contradiction that that is the only possible solution for things to have a consistent result, right? And let's do it now. So let us say the current in both sides is I0 by 2. What is setting the DC bias of this potential? What is this voltage equal to? How was this voltage getting decided? Yeah, again remember, to carry a current in this transistor, there needs to be some gate to source voltage across this fellow, and that is automatically getting developed because of this negative feedback. So this voltage is VB minus VGS of, let me label the transistors, maybe M1, M2, M3, M4, 0, VGS of M1, the current, not by 2. Similarly, what can you say about this node potential? What is this equal to? Again, remember, to carry a particular current in this transistor, M3 needs a particular source to gate voltage, and that is getting set by this negative feedback connection. So that potential is also, or that potential is VDD minus source to gate voltage of the transistor M3 at a current of I0 by 2. And initially we saw that if lambda n is, the channel length modulation is not there, or if it's the lambda is really small, this potential is not getting defined properly. So in practice, what sets this DC potential? Okay, let's say if I say lambda and lambda p are 0, we saw that in the last class this is like having two current sources in series. The in between potential is not defined at all. So in practice, what do you think will happen? We saw it in the last class. Anyone recollect? Okay, is everyone understanding that if I don't consider the channel length modulation, this is like a current source PMOS. I have another current source NMOS. So both are equal or designed to be equal. So this voltage is not defined, right? So in practice, how is this getting resolved? Which voltage? Current? I am saying lambda n is 0, right? Current depends only on gate to source voltage. So this voltage I can have anything, right? Yeah, remember that finally an op amp is not supposed to be used in open loop at all. Why on earth are we designing op amps with infinite gain? What is the reason to design op amps with very large gain? To be used in negative feedback, to make feedback circuits, and the moment you have it in negative feedback, so let us say this is the simplest connection I make now, and you apply a PB here. So what will this potential be? So that's what will set this potential. So I'll just mention that this node is set by the negative feedback finally. I'll say this is set by the DC negative feedback. Okay. And the input whatever bias. Fine. Cool. So then we also considered what happens in if lambda n and lambda p are not 0. So there we saw that if lambda n and lambda p are not 0, if you take this op amp in open loop, what can you say about these two potentials? Again, think about it. This is a asymmetric circuit. I am feeding in a common mode excitation. If the channel length modulation is there, what can you say about these two potentials? Okay, see so many blank faces. See, if I call this potential as some V4 and this is V3, how many possibilities I can have for V4 and V3? So let us say I assume this is less than V3. So I find that V3 is smaller. V3 is the drain voltage for NMOS transistor. So which means the drain current of left side current is smaller or right side current is smaller? With respect to NMOS, it looks like the left side current is smaller. Smaller than right. Now V3 and V4 are not only the drain voltage for NMOS, but also it's also the drain voltage for the PMOS transistor. Now I find that the drain voltage is smaller in the left side. For a PMOS, if the drain voltage is smaller, is the current larger or smaller? Larger. So from the PMOS point of view, what is the condition you get? Left side current is greater than right side current. So what is the only consistent solution? If they are equal, what can you say about that node potential? What will this be? Same as the left side one. So again, this you take in open loop and measure it. If things are all ideal, the same voltage is what you will measure. But in practice, you will end up using a negative feedback loop, and that is what will set this voltage. Okay. Because this is assuming that there is no mismatch between these two fellows, and so on. So in practice, you can't say what this is exactly. Only the overall negative feedback that is, where the op amp is being used, that will determine what that voltage is. Okay. And the last class, towards the end of the last class, we also looked at, maybe I'll copy this. We looked at the swing limits. So I'm sure you forgot. Let's do that. Yeah, and again we recognize that the op amp is going to be used in some kind of negative feedback circuit like this, and ideally remember that for, let me erase this. Yeah, ideally at the inputs of the two gates I'll have a DC bias plus a small signal, and let me call the small signal can in turn be decomposed as a common mode part, differential mode part. So let me call the common mode part of the small signal as VICM. In addition, you will have a differential mode part, so plus VIDM. Now again, you guys know this DC bias plus this small signal common mode, we kind of club it together and call it as some VICM. So let me write that. So this is what is the scenario typically. So strictly speaking, we should be finding the limit on both this VICM and the differential mode voltage. But let us say I use it in this kind of a negative feedback system, and let us say you apply some VB plus VI at the input. So what can you say about the non-inverting terminal potential? It is what? VB plus VI. Assume that this has infinitely large gain for simplicity. What can you say about the inverting potential? That is also same. So then what can you say about the VICM? VICM is the common mode, that is the average of the two inputs of the op amp, which is the average of the two signals, which is basically this. Similarly, what can you say about the differential mode part? That is exactly 0, or I mean in practice very close to 0. So that's why we decided there is no need to look at swings for the differential mode, because finally when you are using the op amp, the actual differential signal that the op amp sees is close to 0. So we only look at the range for the common mode signal, and we started to do that. So let me copy this maybe. So I don't consider the differential mode, I'll only take the common mode and see. So one thing we observed was, if I change the common mode voltage here, what can you say about the currents in the transistor? Yeah, if I change the gate voltages on both sides by the same amount, the current is still going to be same, I0 by 2, I0 by 2. But how is the current remaining the same? So this potential gets adjusted automatically, so as to keep the same current. So here this voltage is, I'll say VICM minus this. So if I keep reducing this VICM, what can you say about this potential? That will also drop. So if I keep reducing this, this will also reduce. So which transistor can go out of saturation? M0. So what is the minimum voltage I can have here? It is the VGS minus VTH for that transistor M0, and we define the VGS minus VTH as overdrive voltage. So the minimum I can have is basically VGS1 at a current I0 by 2 plus the overdrive voltage. Basically this drop, which is always fixed because the current is I0 by 2, plus the overdrive voltage, which is VGS minus VTH for the transistor. Now if I keep increasing this, which transistor can go out of saturation? M1, because I mean M1, M2 both, right? They are identical, because if I increase the gate voltage here, for NMOS transistor that's a problem. So what is the maximum the gate can go to? What is the maximum the gate voltage of an NMOS transistor can go so as to keep the device in saturation? It is one threshold above the drain. Fine. So here the drain voltage is this. Let me write that. So it is VDD minus VSG3. This is the drain voltage. On top of this, I can go one threshold higher. Okay. So I am writing it as VTH1, but it can be VTH1 or 2 because both are identical. Okay. So this is the input common mode range. Similarly, I asked you to work out what is the output swing limit. So did anyone try that? I'm sure no. Everyone was watching something on Netflix yesterday. So let's look at that. So let me erase this. So let's quickly do that. Won't take so much time. Yeah. So now the goal is we want to find out what is the maximum and minimum the output can swing to, because again here you see that in this connection the output is also same as this. So if you keep changing the input or the bias voltage, even the output will swing. So we need to see how much is the maximum the output can go to and the minimum it can go to. So now you tell me, if I keep reducing the output voltage, which transistor can go out of saturation? I have loosely, this potential is connected to only two transistors. So logically speaking, if something changes, only these two fellows might have issues. Now if the drain voltage is dropping, the PMOS transistor, will it have any issues? No. So we'll have issues only for the NMOS. And what is the minimum the drain voltage can drop to? For an NMOS transistor, the minimum drain voltage can go is what? VG minus. And what is the gate voltage here? VICM. So it's going to be whatever VICM you have minus VTH of transistor M1 or M2. Doesn't matter. Okay. So this is clear. If I keep reducing the drain voltage, this can go out of saturation, and the minimum it can go is one threshold below the gate voltage. If you are getting confused, always remember this: the drain to source voltage has to be greater than VGS minus VTH for NMOS. For a PMOS, it is the other way. Source to drain must be greater than source to gate minus one threshold voltage, right? Cool. So now let's look at the upper limit. If Vout starts to increase, so if Vout keeps increasing, which transistor will have issues? M4 or M3? Again, logically speaking, this potential is connected to only two of them. So only one of them will have any issues. So drain voltage is increasing. PMOS transistor, will it be happy? No. So what is the maximum the drain voltage of a PMOS transistor can go to? It is basically the gate voltage plus a threshold voltage. And what is the gate voltage? What is the gate voltage of M4? VDD minus source to gate voltage of M3 at a current I0 by 2. This is the gate voltage, plus it can go one threshold higher, VTH of either M3 or M4, because we have assumed that both of them are identical. So any confusions in this? It's nothing like complicated here. I'm just using this plain old condition. Oops, wherever is it? Yeah, this condition, and writing on the. Okay, cool. So this is basically the input and the output ranges. But in practice, as an end user, I am not interested in this common mode range and the output swings and stuff. I just want to know what is the maximum small signal VI I can apply to my op amp. If I give you these two information, how can I find what is the maximum small signal VI I can apply to the op amp? How can you find it? Why do you say that? Yeah, as he's saying, VICM is, we have found the limit for the input common mode range, and VICM is essentially VB plus VI. So you basically know the limit for VB plus VI, right? And is that all or something else is also there? Which one? No, that's what I mean. Why is plus VD minus VSS is a problem? I mean, we have made sure that the supply of VDD and 0, this is the maximum you can go for the input common mode range so that things are in saturation, right? I mean, what did you mean by when you say VDD minus VSS? Oh yeah, I mean, other condition, but that is, I mean, that's like saying it can be between minus infinity and plus infinity, right? What you told is correct, but a more stricter condition is what we are looking for. Understand? So one he suggested is correct. So this is setting one limit. Is there some other thing that is setting a limit on a Vi? Look at the circuit and tell me what other voltage is equal to VB plus Vi. The output voltage is also equal to, okay, and we also know that the output can only be in this range. So we have two limits set by both of them. So we'll see what will happen. So yeah, VICM as you know is basically VB plus Vi. Fine. So if you want to find what is the limit on Vi, I will simply subtract VB here. So, okay. So this condition says that my Vi minimum is this, maximum is this. Now similarly, I know in my circuit configuration, Vout is also equal to VB plus Vi. No question? Okay. Output is also VB plus Vi. So again, this will set the limit on Vi like this. So okay. So now let's look at the, this is set by the output, this is set by the input common mode, fine. Let's look at the limit set by the output first. Let's look at the lower limit. My output swing limits constraints that my small signal Vi at the minimum it can reach only this much. And what is VICM in the circuit? What is VICM in the circuit? VICM is basically VB plus Vi. Fine. So let's substitute this. So if I substitute this, I get VB plus Vi minus VTH1 minus VB goes off. So basically this limit says that my Vi has to be greater than Vi minus VTH, correct? So this condition here, it says my minimum Vi is this. That is basically meaning that Vi is greater than Vi minus VTH. So do you think this will be satisfied or not satisfied? So this is basically not giving any information, right? This is a always true condition, so you don't have to worry about this thing. Fine. So which means I have a maximum limit, sorry, minimum limit only set by this fellow. Fine. This is the Vi minimum I can have. Fine. Now when we come to the maximum limit, I have one maximum limit set by this, other maximum limit set by this. Okay, so let us say this is Vi max 1, this is Vi max 2. So one equality says that my maximum Vi can be this much, another condition says my maximum Vi can be this much. So what will be the final maximum you will choose? Minimum of the two, right? So here you see the two voltages, they are basically identical. The only difference is in the threshold. So whichever is smaller, you take it. Okay. So the final Vi max is basically minimum of all the maximum limits you have that you get from your circuit. Is it clear? So let's take some numbers maybe. Let me assume that supply is 1.8 volt. I think that's the supply given in your project also. Let's assume the threshold voltage for all transistors is 0.4 volts. VGS is 0.5 volts for all transistors. Okay. So then, can you calculate and tell me what is the minimum Vi? So Vi minimum is this. So what is this equal to? And let's say Vb is 1 volt. Okay. Just plug in numbers and tell me what is VGS1. How much is VGS1? 0.5. All VGS is 0.5. Okay. How much is the overdrive voltage? Overdrive voltage is VGS minus VTH. How much is that? So this is 0.5 plus 0.1, 0.6. So 0.6 minus 1 volt. So this is minus 0.4 volts. And what is the maximum I can have? Let's look at it. VDD is 1.8. Gate to source voltage is what? 0.5. So 1.8 minus 0.5 is 1.8 minus 0.5 is 1.3. So plus VTH. VTH is, how much is it? Yeah, 1.7. And 1.7 minus VB. VB is 1 volt. 0.7. Right? So now if I had to ask you what is the maximum sinusoidal amplitude you can apply to this thing, what will that be? It will be basically the minimum of these, which is basically 0. So the maximum sinusoidal amplitude you can apply is basically . So what we have worked out is essentially the swing limits that you would have calculated all this while for small amplifiers. Why not? Why can it be higher? Yeah. That's what it. The offset is basically VB, isn't it? For this condition, this is the result. What do you mean by offset? I didn't understand. Correct. Yeah, basically, right. So you think about it, the signal we are feeding is VB plus Vi, correct? So this is VB. At the lower limit, I can go to basically minus 0.7, sorry, minus 0.4. At the max, I can go as 0.7. So to have a symmetrical swings, I can only do this. Okay, so I can only do this, and I can't use this portion. Right? You are saying that you can shift this offset here, but that will essentially mean you are changing VB. So which means the numbers will again change. Right? So yeah, as I was saying, this is basically the swing limits that we have been working out. Just that for op amps, this is how we compute. Okay. So let's do that. Hold on. So if you're not convinced, let's actually do it the brute force way, the way you used to do it, and convince ourselves. So this is basically the so the goal is to find, I have an op amp in negative feedback like this. You are supposed to find what is the maximum VA you can apply so that all transistors are in saturation, nothing goes to triode or cutoff, right? And this op amp is basically realized using the 5 transistor op amp like this. So let me copy this. So here, which side is this is the output. Left side is positive or right side is positive? Huh? Left side is positive. Is that okay? So now let's make the connection. So this is the op amp. The connection I have is this. From the output to the negative terminal I am making a connection. So this is plus terminal, minus terminal. So I will basically go on. And to the non-inverting terminal I am feeding in a signal VB plus VI. So here is where I will feed in the gate, DC bias VB plus a small signal VI. So your goal is to find out the limit on VI so that all the devices here are in saturation, none of them enter triode and none of them enter cutoff. Let's do the brute force way, the way we generally do. And how do you go about finding the limits? What do you do? Let's say this is the circuit I gave you and asked you to find the limits on VI so that none of the transistors go out of saturation. What would you do first? Sorry? We need to find all node voltages and all node currents. Fine. So we have the DC operating point and the small signal. So let's do it one by one. We already have written all the DC operating points. So let's finish it. So the DC operating point here at this gate is VB. What can you say about the DC operating point here? Again, remember this is in negative feedback. Let's assume that the op amp has infinitely large gain to simplify calculations. So this potential will also be with respect to DC bias, it is VB. Fine. Let's not consider VI now, only VB we are taking. Okay. So this is also at VB. And what about this node voltage, the tail node? What will be the tail node voltage? VB minus the gate to source voltage required across this. Sorry, I will not write I. Okay, let me write I not by 2. It's fine. Cool. So similarly, this potential DC is also this. So we have marked all the DC voltages quiescent point. So now we are feeding in a small signal VI. Now let's try to write all the incremental voltages and find the currents. So yeah, again assume that the op amp has infinitely large gain. What will be the small signal voltage here? If at this terminal the small signal voltage is Vi, what will be the small signal change here? Vi. So here obviously it is Vi. Okay. So here is where I am feeding Vi because of the op amp's gain. This is also as close to Vi as possible. So again, for simplicity, we are assuming RDS to be infinity for all transistors. If you don't want to do so, you don't want to do exact calculations and make it messy. So till this point, hopefully it is clear. Small signal voltages at both the gates is Vi. What can you say about the small signal voltage at this node? Again, assume RDS is infinity for all transistors because let's do quick calculations. Huh? Vi by 2, Vi by 4, 2 times Vi or 0. How will you find it? Huh? Yeah, let's do the small signal thing. So I told that the RDS of all transistors is infinity. So what is the small signal current flowing here? RDS of this transistor is how much? Infinite. So what is the small signal current? 0. So the current here is 0. What is the current in this branch? If I call this as some Vx, what is the small signal current here? Gm into Vi. What is the current here? Same. Sum of these two should be equal to what? Sum of these two currents must be equal to this current. And what is this current? 0. So what is Vx? Right? So I know that this potential is Vi, so I will directly add. Okay. So now can you tell me the incremental current in the transistors now? How much will that be? 0. Gm VGS. VG is same as Vs in our approximation. So the incremental currents are all. Okay. Again, this is 0 because we have assumed the RDS to be infinity. In practice, it will be very small. If we included the number, the final results will change slightly, but it's okay. We don't care that much. Okay. So yeah, now let's find the small signal voltage here. What can you say about the small signal voltage here? Hmm? 0. So what can you say about the small signal current through the PMOS transistor? 0. Why? So the incremental current through the NMOS must be same as the incremental current through the PMOS. So the incremental current through the PMOS is 0. So the 0 current is flowing here through some impedance. What will be the voltage? 0 current flows through an impedance. 0. So incremental voltage here is Is this clear? Remember, if the current flowing here is some Ix, what will be this node potential? If let us say this is some general Ix, the current flowing upwards, then what can you say about this node potential? Ix into? Okay, I have a current flowing here. I want to find the voltage here. What do I need to find the voltage? The equivalent resistance there. What is the equivalent resistance here? 1 by Gm, okay, parallel RDS, whatever. So what will be the voltage then? Ix by Gm. And in our case, what is Ix? So voltage is fine. So now we have written all the incremental voltages and currents. So firstly, what are the incremental currents in the circuit? 0. So do you have to worry about transistors going to cut off? Yes or no? Why? Yeah, I have. What is the operating point current in the transistors? What is the operating point current in the transistors? I0 by 2, I0 by 2. Now due to the small signal excitation, there is no change in the current. So will the transistors go into cutoff? So that's one nice thing. So you don't have to worry about cutoff. So let me erase this. So I'll just say it's right. So what is the only thing you need to worry about now? Whether it can go to triode region or not. So let's quickly do that. So how many transistors we have here? 5 transistors. We look for all 5 transistors. So first tell me for which transistors I don't have to worry about it entering into triode region. Is there some transistor here which can never enter into triode region? M1. Why M1? No, incremental voltage is Vi. Why M3? Remember, gate and drain are shorted. So VGS is same, drain to source voltage. Yeah, it's definitely greater than VGS minus VTH. Fine. So we don't need to worry about M3. Any other transistor? Even M2, if you look at it, the gate and drain are shorted. So even for M2, you don't have to worry about it entering into triode region. Okay. Because remember, gate voltage is same as drain voltage. So which means my VDS is equal to VGS. So then it follows that it can never enter into triode. So I will say M3, M0, I don't have to worry. Put a smiley. So now let's look at remaining transistors. I need to look at M1, M4 and M0, only 3 of them. So let's look at M1 first. For M1, what is the condition to be satisfied for it to remain in saturation? The maximum, okay. This fine? Okay. Sorry. Yeah, sorry. It's the other way around. The difference between gate and drain has to be less than a threshold. That is, the gate voltage can go one threshold higher than the drain voltage. That's the maximum. Okay, that's what I have rewritten. So if I plug in the values, what do I get? I have VB plus VI as the gate voltage. Drain voltage is VDD minus VSG3. I will not write the currents with VGS for simplicity. Which one? So it says my VI is less than whatever VDD VSG3 plus VTH1 . So nothing complicated. I know the total gate voltage, total drain voltage. I am just writing the condition for the transistor to remain in saturation. However you remember it, you can do. Right? Drain to source voltage must be greater than VGS minus VTH. That is the final condition. So this is one condition you get. And this is for M1. Let's do for M4. We'll have to make some space. Yeah, if I do it for M4, what do I get? What is the condition for M4? Yeah, I need to have the other condition. Again, the same thing. However you remember it, we can do it. So if you put in the values, what is the drain voltage for M4? Total drain voltage. Drain voltage. VB plus, fine. Gate voltage is whatever that VDD minus VSG3. This should be less than mod VTH4. So you work out what is the limit from this. So that will be same as VS should be smaller than, you will get the same thing, VDD minus VSG3 plus VTH4 minus VB. In just plain algebra, I don't have to worry about it. This is the result. What is the remaining transistor then? M0. So do it for M0 and tell me what is the condition you get. Can you write and tell me what is the final limit you get? Huh? Oh, assume that it is some VGS 0, right? Okay. Please work out, this is what you should have got. Okay. Again, overdrive is VGS minus VTH. When I say V overdrive 0, it is VGS 0 minus VTH 0. Clear? So again, now you can basically stare at this page and the previous page, and you can convince yourself that the limit we calculated here is same as what we calculated here, because I just copy pasted from there. So instead of doing this kind of calculation for an op-amp, we basically do it this way, because think about it, you are selling an op-amp to a customer. The customer can use the op-amp in any kind of negative feedback configuration. Now if you had to resort to this method, You have to give the full schematic to the customer, and then the customer has to put the proper feedback connection and then work out all the node voltages, incremental operating point, blah blah blah. If you have, let us say, 10 transistors in your op-amp, for all 10 transistors he has to go and work out, and then he or she will just go mad, right? So instead we do the following. We notice the fact that an op-amp is never used in open loop. It's always meant to be used in closed loop, right? So which means that the differential mode swings will be 0. So you can only have common mode swings. So you mention what is the limit on the common mode swings. Similarly, what is the swings you can have for the. So if you know these two, you can actually directly compute what is the limit on your Vi in one shot like this. So that is why in practice, if you open any datasheet for an op-amp, I think I probably have opened something. Yeah, this is an op-amp from TI. I don't know if it's visible. I can close this fellow. So you can see one of the specifications they gave is this input common mode range, the first column. Okay, I don't know how we can point with this, but yeah. So they have given it to be whatever, right? Plus or minus 13.8 as the minimum. Typical number is this, blah blah blah. And similarly, they'll specify what is the output voltage swing. Not able to highlight it. Under output characteristics, the first row you can see. Okay. So when they are operating at a supply of plus or minus 15 volt, that's what they have written VCC. The typical number they have is this plus or minus 12.2. So that's what. This is what is usually specified, and depending on what configuration your circuit is going to be, you can basically work out what is the limits. So for example, let us say I give you this. Say some op-amp says that the common mode can go from some voltage Vm1 to Vm2, and the output swings can be from say Vm3 to some Vm4, and you decide to use the op-amp in an inverting amplifier configuration. So first of all, should this be connected to ground? Remember, this is going to the gates of the differential amplifier. Should this be connected to ground or something else? Huh? If I connect it to ground, what will happen? Yeah, there will be no biasing. So this should be connected to some bias voltage. Let us say that is some VB2. Similarly, at the input side, let us say I use some VB1. On top of it, I apply small signal Vi, and let us say R1, R2. So now can you help me calculate the limits on the bias voltage VB2 and the small signal voltage Vi? How will you go about doing this? You tell me what would you do first, right? You don't have to calculate. Let us say the op-amp datasheet says that my input common mode can be in this range and my output can swing in this range. This is the only detail given to you, and you know that you are going to take that op-amp and make an inverting amplifier, let us say. So how would you make sense of this result to get limits on Vi and Vb? Okay, great. So first he is saying we'll find V out. Okay. So or before that itself, right? We have been given only on VICM and V out. So what should you do here first? You find VICM in your circuit, correct? Because I only know information on VICM and V out. So you find what is VICM in your circuit. Make sense? And what is VICM in this circuit? Remember, VICM is the common mode input, that is essentially the average of the inverting and the non-inverting terminals. What is the average potential of these two? VB2, fine, because again assume that this is almost close to VB2. So I know that VICM is equal to VB2. Okay. So directly I get the range for VB2. That's all. Fine. Is clear? So next, I know the limits on V out. So we can try to find what is the total V out here. So the total V out will contain the DC operating point and the small signal. So let's try to find both. So maybe we'll copy paste this. Yeah. So let's now look at only the DC bias. So I'll not assume that I have a small signal Vi. What will be the output DC bias? If I apply VB1 to this op amp and VB2 at the non-inverting terminal, what will be the output voltage? Come on folks, it's not that complicated, right? Assume that it's an ideal op amp. Come on, this should have been a gate question to you, right? How did you solve then? Minus VB2 doesn't, okay, tell me, what is it? It's not correct, okay, and then? Partially correct. Okay, work out and tell me. Minus R2 by R1 into? No, that's not correct. Come on folks, minus 1 marks in gate for you. Okay. Yeah, correct. And then? Correct. Yeah. How do you say this? How did you get this? Yeah, again, simple thing is you have two inputs, use superposition. So let us say I short this fellow. I feed VB2 here. So from this here to here, what kind of amplifier is it? A non-inverting amplifier. What is the gain for non-inverting amplifier? That's what you got here. Now do for the other guy. So you short this fellow. You have only VB1. What is the output? Okay. Should not be solving it right now. We should be looking at these things and able to say this. Okay. So this is the total DC bias. And one thing to notice, let us say here, if I choose VB1 to be equal to VB2 equal to some V0 or some VA, what will this simplify to? VA. So basically, if you keep all the voltages to be same here, even the output will also be at the same bias voltage. Okay. I mean, that's why I think even in your project, I am sure the bias voltages were chosen to be equal. The bias voltage for the input and the one connected to the non-inverting terminal. So this is only the DC part. Now if I apply a small signal Vi, what will be the output? I mean, I already know what is the response if I apply VB1, VB2. Now in addition to it, Vi is applied. What will be the output? Minus Vi into? Is this clear? Inverting amplifier, Vi is the input here, minus R2 by R1 times Vi. Okay. So now you know what is V out, and V out is constrained in this range. So we can go and find what is the range for VA. Right? That's all. So that's how in practice you kind of use this information and try to understand what is the range of voltages you can apply at the input and for your bias voltage. Okay. So that is the reason why we kind of try to calculate the input common mode range and the output swing limit for an op amp. This is true only for op amps because we know that it will be used in negative feedback, and in negative feedback the differential mode signal will be 0. So for the input you only worry about the common mode, and for the output you look at the total output. Great. So okay, so then is this till now, is it fine? Whatever I have told. So if this is clear, let's move on. Oops. Let me copy this. So this is the op amp or the OTA we have so far. Okay. And what is the small signal gain of this differential mode gain? If I if I label the transistors, what will be the small signal gain? Differential mode. GM of which transistor? Yeah, I have labeled the transistors, right? GM either 1 or 2, both are identical. So I'll just say it's 1 times. Yeah, RDSP, RDS of 4. Like I mentioned, you work out what is the output resistance with the channel length modulation included for the NMOS. You will find that this is indeed approximately RDS2 parallel RDS4. So this is what you have, and basically this is basically like a GM RDS of a transistor. That's going to be really small in practice, say 20 or 10 or something. Now if you want to get more gain, because you want to get infinite gain finally. So to increase the gain, what do you suggest we can do? Okay, I can increase GM, but whatever you do, how do you increase GM? Increase VGS. How do you decrease VGS in the circuit? Let us say, look at the operating point alone. Let's say that's a good exercise. Let us say this is a transistor, this is the op amp configuration. I applied a bias voltage. I find that the transistors here have some GM. His suggestion was, let's increase the GM of the transistor to increase the gain. Reasonable suggestion. So my question is, how do you increase the GM now? If I increase the W by, let's say increase it by 2x, how much will the GM increase by? Why? Remember, I have multiple expressions for GM. Okay. This is 1. This is 2nd. This is 3rd. So from this equation, it looks like, if I increase W, nothing is going to change. From this expression, it looks like it will go by square root 2 times. From this, it looks like it will go by factor of 2. So who is telling the truth? Why not the third one? It looks nice, a fraction. So ideas, all equations are giving the correct information. You are interpreting it incorrectly. That's all. So remember that if I change the size here, what can you say about the current in the transistors? Will it change or will it not change? Why will it not change? It is biased with a constant current I0, and as long as both sides are identical, the current is going to split equally as I0 by 2, I0 by 2. So you go and increase the size of this by anything you want, the current will be I0 by 2, I0 by 2. So which means what will change to make the current I0 by 2? The VGS will change, in particular this voltage will change. So here this guy is constant, but this will change. And how much will VGS change? Remember, ID is half mu COX W by L into VGS minus PTH whole square. My ID is changing or not changing? It's not changing. So it's 1x. This factor is changing or not changing? By 2x. So how should VGS change? VGS, this term should go as 1 by. Okay. So VGS goes as 1 by root 2. So how will GM increase by? VGS reduces by a factor of root 2. Is that clear? Maybe if it's not clear, I'll write it. So VGS minus PTH reduces by a factor of root 2. Okay. If this reduces by a factor of root 2, what will happen to GM? By a factor of root 2. Okay. Yeah, but you see that how much is root 2? This like 40% increase in the gain, right? Let us say right now we have 20. I want to get 200. This might not be reasonable. So what is another suggestion? What is, I have some quantity. I want to increase the quantity. What do you do? I gave you 2 chocolates, man. You wanted more chocolates. So how can you get more chocolates? only if I give you more chocolates. So have some quantity, I need to increase it. I need to either, what are the two operations I should do? What are the mathematical operations I can do to a number to increase it? Basically, I can add or multiply. So, and here adding gain is easy or multiplying gain is easy? Huh? Multiplying gain is easy, but why is that so? I mean, okay, maybe I convolved it so much. See, I have some gain from this stage, right? I am saying this is not enough. I want to increase the gain. So what is one suggestion? Yeah, that's what, whatever you do, right, I am saying, right? That's what he suggested. Whatever you do, it's not going to go so much. So I cannot simply use this. So what can you do? Okay, I can basically put one more stage and cascade. Fine. So what kind of stage do you think I can put here? Okay, I have a V out. Okay. So if I go into, I need to use another amplifier. That much is clear. So this is taking two inputs or one input? One input. And how many outputs you should give? One output. What is the simplest thing that you know that can make this common? Common source, common drain. What means if I say something, you change it to it. Huh? Common source or common drain? Common source. Okay. So basically, let's try to put a common source. Fine. So what is the incremental gain of this fellow? Let me call this M5. What is the small signal gain of the second stage? GM5 into RDS5. Fine. Now where do I take the output now? From the drain of the transistor M5. Is clear? So tell me which is the positive terminal, negative terminal now? I mean, let me make it. I have A and B. Which is positive, A or B? B. Why? Because you want to be positive. Huh? Yeah, again you can find, right? Let's say I increase this voltage. What will happen to this voltage? What will happen to the drain voltage if I increase the gate voltage? Come on, people, please wake up. Let's finish and move on. If I increase the gate voltage, what will happen to drain voltage? Decrease. Awesome. So then what will happen to this voltage? Drain voltage will? So gate voltage increases. This will? So what is the negative terminal here? A is negative. Okay. So this is negative. So as usual, B positive. Okay. Fine. So yeah, now let's take the circuit. Let's stare at the circuit. Look at this part in particular. So what I have essentially done here is I have pumped in a current to a drain. I am pumping in a current to the drain of a transistor and assuming that the gate voltage will get set automatically. Do you think that is possible? Yes or no? No, right? So do you think this will work or what's happening? Is the problem clear? If I look at only this part, which is the one I have drawn in red or whatever color it's showing there, I seem to have a case where I am pumping in a current source to the drain of an NMOS transistor. And remember, the current in a transistor depends majorly on the VGS. So how is the gate voltage getting set properly here? Sorry? Gate and drain is short. Why? This is the gate, right? And this is the drain. If you short the gate and drain, yeah, it works. But that's not what I am doing in the amplifier, right? I mean, with respect to small signal gain, definitely we seem to have done something better, right? Gain has increased. But looks like it's not going to get biased. So how do you think it will get biased? How can we do this? What will you, gate is connected here, isn't it? You can't change anything. No, I'm not saying you cannot add anything more. This is the circuit. Okay. So in practice, what do you think will happen? Sorry? No, that's what. You cannot add any more biasing to this, right? Because gate has to be connected here. So whatever you do, right, you can put any voltage. I mean, if you want to do something like this, but how will you ensure that this voltage is sufficient to carry this current I2? You understand the confusion? You can put any bias voltage here, but that's not going to solve the problem. Did we see a similar situation somewhere before, where the operating point was not getting set properly? For M4 in the 5 transistor OTA. So what was happening finally there? So here again, this is an op amp. An op amp, remember, is never meant to be used in open loop. So where should I use it? In negative feedback, some kind of closed loop system. So let us say you do that, right? So this is negative terminal, positive terminal. Again, I'll take the simplest connection. I am going to do this. Okay. So here I am going to feed in a bias voltage VB. So here if I make this connection, from the output to the negative terminal, I should short. Output, I'll be shorting this way. So this is what I'll have. So now tell me what's happening. Now do you think the bias voltage is set? I mean, how do you check if the bias voltage is properly getting set or not? I mean, from whatever you have learned so far, to bias a transistor with a particular current, what is the fundamental principle you use? I mean, what are the different kinds of way in which you are biasing with a constant current? I mean, anything. Tell me something. The way in which you biased. Someone was saying drain feedback, source feedback. What do you do? What is the underlying principle in all of them? You send something and feed it back, and that's what a negative feedback does, right? And to see, let us say I gave you this, right, and simplest circuit, right? So let's just look at this and wrap up today. How can you prove me that this voltage is getting set to a point wherein the current in the transistor is equal to this? I am saying it is not getting set. How do you disprove me? Let us say the current in the transistor is higher. Then what will happen? This voltage will start to drop, which means the drain current will reduce. A negative feedback is there. So here, to see if the gate voltage is properly set, what can we do similarly? Let's say that the current in the transistor here, let's say it's I5. Let's assume I5 is greater than I2. So if I5 is greater than, or let's say I'll put the other way, I5 is less than I2, anything is fine. So what will happen to this voltage? That will increase. So this increases, that increase goes here, this increases. Then what can you say about this voltage? That will also increase. Fine. Again, if you want to go step by step, the gate voltage of M1 increases. So the drain voltage of M1 reduces. So this reduces. Gate voltage of M4 reduces. Drain voltage of M4 increases. So which means gate voltage of M5 increases. What can you say about the current? That will increase or reduce? Decrease. Gate voltage increases, current will? Fine. And is that what you wanted? Because I5 was smaller, so now you see I5 increases. Okay. Is this clear? So actually, if you look at this one, you can actually recognize this. thing is fine, whatever I told. So I'm going to erase it, that's why. So what you can actually think of the setup like this, right? See, I know I can bias a transistor either by feeding the drain and connecting it to the gate, or I sense this guy, pass it through a gain and feed it to the gate. Both are same, right? I mean, if I can have an amplifier A in the feedback. That was also something you can do. When A is equal to 1, this is a special case. Now you look at the scenario. I am sensing the drain voltage, giving it to an op-amp, right? This is the amplifier. Fine. This entire thing is an amplifier, sensing the drain voltage, amplifying it, and feeding it to the gate. So basically, if I were to do this, so let us say this is the amplifier. So the one in green is the amplifier. Right? So I can think of it like this. So let me make this small. So this is as though I take only the second stage, and then what do I do? I take this fellow, connect it to an amplifier, and here is where I connect the VB of whatever, 1 volts or whatever. So the moment you put the entire thing in negative feedback, you see that the DC bias is also set by some kind of negative feedback action. Okay. And in fact, let's see if I have. And in fact, I know for a fact now that this has a negative feedback around it for setting the DC bias. What about this transistor? How is the DC bias set? How is the gate voltage of M3 getting set? I0 by 2, but is it, is pumping a current I0 by 2 alone is sufficient, or something else is being done? Yeah, this feedback is there, right? Same, the water feedback is there for this fellow. And now you look at, let us say, M2 also. Let's look at M2. For M2 also, if you look at it, the drain voltage of M2 is getting sensed. That is getting amplified. Amplified signal is kind of getting fed here. It's getting buffered and fed here. That is, I'm sure you saw this also. You sense at the drain and you can feed at the source also. Right? You can have something like this. Correct? Now if I look at M2 alone, so I have the second stage M5 here, fine, that is amplifying it. That amplified signal, I am giving it to M1, buffering it, and then feeding it to the source. Does it make sense? So this is the sensing at the drain, feeding at the source configuration. You sense at the drain, and you feed it back to the source, and in between this you have an amplifier essentially. Okay. So even for M2, if you see, there is a nice negative feedback. And what about M4? How is its bias getting set? What kind of feedback here there is? Can you tell me what terminal is getting sensed? We are sensing at the drain, clear? And what are we controlling later? Gate. You see that this is getting sensed. We amplify it. Amplified signal goes here. It gets further amplified here and then goes there. So this is again sensing at the drain. We are amplifying it and feeding it to the gate. So this also has a negative feedback around it. And look at M1. What's happening to M1? How is the what kind of sensing is happening for M1? I'm sensing at the drain. and this signal is sensed, amplified here. Remember, I am taking the, I am feeding the signal to the gate of the PMOS, taking it from the drain. There is an amplifier here, and this is further getting amplified, feeding it back to the gate. This clear? So every transistor here is properly biased by one or the other kind of negative feedback biasing scheme we have been studying all along. So it's not like randomly, we taught these things to ask questions and, like make you lose marks in exams. It's all for a reason, because eventually these are all being inherently used to set the bias point of all transistors in this op-amp. Okay. Please remember, at the end of the day, a transistor's gate voltage needs to be biased using some kind of negative feedback so that its current is constant to whatever value you want. And any op-amp you see, you should be able to identify and see when it is a negative feedback, where is it getting sensed, where is it getting controlled for each transistor. Okay. So stop here and